An impromptu video. So honestly, I didn't really make any specific plans for this one, but I've been getting questions about basically things related to actually watching videos and how you can use those to learn from them. And it kind of just occurred to me that I think as teachers, we're accustomed to just assigning work online and just assuming that you know how to do it. Um, because essentially that's what we've been exposed to. Like that's how online classes work for us. We just get the work. Maybe we get some videos assigned. We have to watch the videos. We got to figure it out. Um, what I'm finding is that some of my students are okay with that, and like they've already got the skills that they need, and they can more or less figure it out. Um, but some of the students really don't understand what it means to learn from a video. So in light of all of us being on lockdown, I thought I would kind of make a video where I actually go through someone else's video and sort of make comments about what you should be doing as a student to actually learn from it. In the future, I'll probably make some of my own videos with instruction, and what I tell you now applies to my videos too. So in other words, even though we're about to look at someone else's video, the comments that I make about it would apply to even a video that I make as well. So let's take a look. All right, so for example, this is a video on Venn diagrams and set operations. It just so happens that this is going to be something that my geometry classes use because this is in the probability and data section of geometry for Common Core and for Georgia. So if you're not in geometry, no, this content isn't specifically going to apply to you, but you'll still find that it shows up in other courses. And again, the general comments that I make about how to watch this video ought to help. So let's get going.
Welcome to a lesson on Venn diagrams and set operations. The goals of the video are to define a Venn diagram, use Venn diagrams to show relationships among sets, and also to define set operations. A Venn diagram is a visual...
All right, so I'm going to pause it right there and kind of take a step back here to the very first page. So a lot of times videos just dive straight into the topic. This one's kind of nice in that they actually give you a goal. So they tell you, hey, we're defining a Venn diagram. We're going to show how to use those Venn diagrams to show relationships, and we're going to define set operations. So you should pay attention to that, because if you come away from this video and you don't know what those things mean, then you didn't get out of the video what the person speaking, what the teacher, the instructor, the author even expected you to get.
Sets, and also to define set operations. A Venn diagram is a visual diagram that shows the relationship of sets with one another. The set of all elements being considered is called the universal set, and is represented by a rectangle as we see here. The complement of A is the set of all elements in U, not in A. Or using set builder notation, the complement of A is the set of elements X, such that X is an element of U and X is not an element of A.
All right, so I'm going to stop right there. And first, you'll notice with some of these videos that if you're being instructed, the person that's actually doing the talking is just going to walk you through the content. In this case, they have not really made any clear assumptions, or maybe I should say they haven't made it clear what they think you should already know. They're just running through this video, and you're supposed to watch it and pick out the information. So, he starts with saying a Venn diagram is a visual diagram that shows the relationships of sets with one another. Okay, that's great. If you don't know what sets are, you're not really going to understand what that is. A Venn diagram, even, you got to pay attention to the fact that everything that we talk about in this video is going to be a Venn diagram. The set of all elements being considered is called the universal set. There's that set word again. You got to know what that means, and is represented by a rectangle. That means the rectangle that you see below, it represents the universal set. That's why there's a U in the corner in the rectangle. The complement of A, and that A with the mark there next to it, is a set of elements in U but not in A. U being the universal set, A being whatever's marked A, And then it gives you some notation down here, as he referred to it as set builder notation. That's a lot of information on one page. And what a lot of my students do is watch a video, they just go through it, and they don't even pay attention to the fact that this was a page where you needed to take notes. This is a page where you need to ask questions. This is a page where you need to pause the video, and you might actually have to look up what some of these things mean. So he's going to start showing examples of what sets are, but notice he didn't specifically define them here. So just as we continue, keep in mind that you could right now be Googling like what set means in terms of mathematics. I can tell you think of it as just a list of numbers. It does not matter what the list of numbers is. This is abstract. It can be any list of numbers. The point is a set is a list of numbers. The universal set would be the entire list of numbers, whatever you're talking about. And then basically what we wind up doing here is we'll take that universal set, which is like a whole list of numbers, and we'll start cutting it into smaller pieces. And those smaller pieces are where you start seeing like this A and the complement of A. This set builder notation down here is something else that tends to throw people off. And again, this is where you might have to look up what these symbols mean. What I can tell you is the complement of A is the set of elements in U, but not in A. This right here, this syntax that follows tells you exactly the same thing. The complement of A equals X, meaning X is going to be like your numbers in the set here. So it's equal to X such that X is contained within the universal set, and X is not contained within A. In other words, if it takes A and the complement of A to make up the whole universal set, so you can think of it sort of as like A plus the complement of A has to be the universal set. I'm not literally talking about addition here, just think about that like in your head. Picture that. If I put A and the complement of A together, I've got the whole set. What this is telling you is if you see this symbol, it means it's actually within the set. If you see this symbol, it's not in the set. So now if I read through this again, all this is saying is the complement of A, meaning everything that's not A, is whatever numbers in your list, that's what this X is talking about, are within the list, your universal set, and not in A. So I just said a lot right there, and honestly that's kind of the whole point that I'm making out of this video. Even with me speaking through what I just explained, some of you may not understand what I just said, and that's okay. Pause it, go back, rewind. You can send your teacher a question and say, hey, what was meant by this comment? Don't just watch the video straight through and expect to understand what it's saying without having to do a little bit of work on the back end to understand it. Well, let's continue.
So if we let the universal set be the integers 1, 2, 3, 4, and 5, and A was the set containing elements 1, 2, and 3, then the complement of A would be the elements in U that are not in A, so it would contain the elements 4 and 5.
I'm going to stop right, there we go. I'll stop right there. So, sometimes seeing an example makes things a lot more clear. He just made this up. So the universal set here, U being the set containing 1, 2, 3, 4, and 5, he just made that up. That could be 1, 2, 3, 4, 5, 6, 7. It could have an 8 in there. It could have a 12. It could have anything you wanted to have. In this case, 1, 2, 3, 4, 5 is what you're given. A, if I say A is 1, 2, 3, then the complement of A has to be whatever numbers are left over up here in this universal set. So in this case, 4 and 5. So if A is 1, 2, 3, the complement of A has to be 4 and 5 because together they have to be 1, 2, 3, 4, 5. Now, what I just said is precisely what I was saying when I explained the words down here, but I'm guessing most of you are going to get more from that example than you did the words. The problem is if you're given a problem like an actual exercise or something to do, sometimes they'll actually give you the wording down here and expect you to be able to interpret that. So take what I said before, rewind if you have to, and compare what I said, what I was explaining, with the syntax down here, these symbols that you see, the mathematical symbols, and compare that to the actual example that you just got.
Elements 1, 2, and 3 would be inside set A, and the elements 4 and 5 would be outside circle A. Set A and B are disjoint if they do not share any common elements.
He jumped right there from the previous slide and kind of just flew through it. So again, this is where you might have to kind of go back and note what he just did in that last example, because now he's talking about a totally different idea. Yeah, it's still Venn diagrams. Yeah, we're still talking about sets, but the point is not for you to watch this 6.5-minute video and think that you only have to spend 6.5 minutes on it. It may take you longer. In fact, I would be surprised if it didn't take you much longer. It's not uncommon to have to stop and rewind a video 3-4 times before you actually understand it. And that's what learning is about. You shouldn't start the video in the beginning and just expect that you can go through and remember it all, unless you've got a photographic memory. And I don't know of any of my students that do. There's a very small percentage of the population that does. And if that's you, great. You can sit back and reflect on everything that you just heard. But for most people, that's not going to be the case. So you have to go through the videos carefully.
Not overlap. So here, if the universal set was a set containing 1, 2, 3, 4, 5, 6, and set A contained the elements 1, 2, 3, set B would not be able to contain 1, 2, or 3, but it would have to contain elements within the universal set. So maybe B would contain 4 and 5. So for the Venn diagram, 1, 2, and 3 would be inside set A, 4 and 5 would be inside set B, and 6 would be outside both circles.
All right, so I'm going to stop it there just to explain what he just said. So disjoint sets, and it actually has a pretty good definition. So it says set A and B are disjoint because they do not share any common elements. So again, remember, the universal set, universal, like your whole universe, your whole world, everything you're dealing with, is in this box. It's in this rectangle. All your numbers have to be in the rectangle. But if you've got disjoint sets, what it's saying is, all right, I've got this huge set of numbers. In this case, it's only 1 through 6. Could be much bigger. And I'm going to essentially break them into pieces, like different chunks of the set. If they're disjoint, that means that my little smaller sets that I'm making, that I'm breaking apart from this bigger universal set, they can't overlap anywhere. So that's why he said, look, if A is 1, 2, and 3, and he even marked it inside the circle for A, if B is disjoint, that means B can't have 1, 2, or 3. But notice B didn't have like a 7 or an 8 or a 9 because it has to still be within the universal set. So any numbers that you pick here have to come from this bigger universal set. If A is 1, 2, and 3, then you're left to pick with 4, 5, and 6 for B. In this case, he said, all right, well, B is 4 and 5. Cool. So I put 4 and 5 in for B. So I've got 1, 2, and 3 that are A, 4 and 5 that are B. There's no overlap there. They don't have any numbers in common. And I've still got to look at my universal set, though, because my universal set had a 6. Well, 6 is in the universal set here. It's in the universe. It's in the box. So 6 has to go in the box somewhere, but you can't put it inside A or B because it doesn't actually show up inside A or B. And by the way, this again is a Venn diagram, and this is just a visual way of interpreting these sets that you see up above.
In this diagram, B is a proper subset of A. This means that B is a subset of A, but B does not equal A. Using the symbols discussed in the previous video, we could say that B is a subset of A, and B does not equal A, therefore B is a proper set of A.
Okay. Now we're just layering it on here, and we're going deeper into the math, and if you didn't actually understand the very beginnings of what we'll call very basic set theory here, then you're going to be lost if you start trying to understand what these proper subsets are. Make sure you understand the first few slides first before you then try to wrap your head around this. Because basically what he's saying now is you got a universal set, what's in the box. We've got an actual set in here, so like A, but you could then take that set A and break it into even smaller pieces. And that's where subset comes in. So B is a proper subset of A. This means B is a subset of A, but B does not equal A. So in other words, B is going to share some numbers with A. So like he's not writing it on here, but for example, if A was 1, 2, 3, B could be 1, 2, or B could be 2, 3. It can't be exactly the same thing because if it was, it wouldn't be part of A, it would be equal to A. So in order for it to be a subset, it has to have some of the elements, the numbers that make up A, but it can't equal A completely, which is why you see B shown as a smaller circle inside A, which is a bigger circle, inside the big box, which is your universal set. Down here, it says that B is a subset of A, and B does not equal A. So, therefore, B is a proper subset of A. Alternative symbol would be this.
And instead of using this symbol for a proper subset, sometimes you'll see this symbol here used. So if we let the universal set contain the elements 1, 2, 3, 4, 5, 6, and let's say set A contains 1, 2, 3, and 4, set B would have to contain some of the elements in set A, but not all of them because they're not equal. So maybe set B would contain 1 and 2. So we'd have the elements 1 and 2 inside B that are also inside set A. 3 and 4 would be outside set B but inside set A. And then 5 and 6 would still be in the universal.
Okay, so again, just really quickly here. Universal set is 1 through 6. That means 1, 2, 3, 4, 5, 6 all have to be in the rectangle. A is 1, 2, 3, 4. Okay, awesome. In order for B to be a proper subset, it has to be a smaller chunk of A. So notice in this case, B actually contains elements that were in A. So B has 1 and 2 because B is within A. So the only thing B could have been is something made up of these numbers that it tells you are A. A is 1, 2, 3, 4. So B has to be some combination of those numbers. In this case, it's 1 and 2. So you see 1 and 2 marked inside B. Notice it's still technically within A on this picture. Again, how the Venn diagram works. It's within A, but more specifically, it's within B. So you know B is just 1 and 2. Excuse me, but A is the 1 and 2 plus the 3 and 4 that we put out here on the outside. But then your universal set had 5 and 6, so they go outside the circles within the box.
And if we have equal subsets, that means B is a subset of A and B is also equal to A. So all the elements in A and B are in the same circle. So the universal set was 1, 2, 3, 4, 5. If set A contains 1, 2, and 3, then in this case B also contains the elements 1, 2, and 3. So we'd have 1, 2, and 3 here, and then outside A and B would be 4, 5, and 6. So if A is equal to B, we can say that A is a subset of B and B is also a subset of A.
Okay, so, and again, this is where you just have to be careful with the terminology. So in this case, in order for something to be a subset, it just has to contain elements that are in the other set. So if your subsets are the same, then you just say they're equal. So in this case, your universal set is 1, 2, 3, 4, 5. Side note, and this is kind of what I was saying in the beginning where you have to pay careful attention to these videos. He made a mistake here. He's been using 1, 2, 3, 4, 5, 6 the whole time. And notice here, he put the universal set as 1, 2, 3, 4, 5, but then here he actually included the 6. That's an error. And that is where you watching this video have to pay attention to things like that. This isn't where you like shut down and think, oh my gosh, I don't know what's going on. This is where you, as a person learning this, actually get some confidence and say, well, wait a minute. Based on everything we've done so far, he's been putting anything left over in this universal set outside in the box. Well, now he just like invented a number. That's an error. That's okay. You're going to run into those. And that is a word of caution when you're watching videos like this online. You've got to be careful and pay attention. If you ever watch two videos about the same thing and they seem to be contradicting each other, that would be a great example of where you should like focus in on whatever the contradiction is, and either A, like look it up yourself and try to figure out why it seems to be contradicting, or B, that's a great opportunity to actually send that to your teacher and say, hey, trying to figure this out. This video says this video says that. Can you please explain? So moving on, if A equals B, then A is a complement of B, and B is a complement of A. Sorry, I just used the wrong word there. You'll notice that happening in videos as well. Sometimes people will say the wrong word and then they have to correct themselves, and that's okay, because we can't just keep remaking videos over and over again and hope that we eventually get it to be perfect. So if A equals B, then A is a subset of B and B is a subset of A.
The intersection of A and B is the set of elements in both set A and set B. Using symbols, we have A intersection B is equal to all the elements X, such that X is contained within A and contained within B. So the universal set is equal to 1, 2, 3, 4, 5, 6, and we have set A equal to 2, 3, and 4, and set B equal to 3, 4, 5. We can see that sets A share the elements of 3 and 4, so that would be in this region here. So 3 and 4 would be in this region here. And set A also contains the element 2, so there would be a 2 here. And then set B also contains the element 5, so we'd have a 5 out here. And that leaves the elements 1 and 6 in the universal set.
So this, I think, is where you start seeing how Venn diagrams can be pretty helpful, because when you look at the Venn diagram, at least for me personally, it's a lot easier for me to look at that Venn diagram and visualize where the numbers are located versus going through these sets as they're listed in set notation up here. So cool, the universal set is still 1, 2, 3, 4, 5, 6. A is 2, 3, 4. B is 3, 4, 5. But then you have to actually think to yourself, all right, so now like where do they overlap? Okay, 3 and 4. And then you see that, and then you can say, all right, well, 2 is in A, 5 is in B. Neither A nor B have 6, and that's in the universal set, so I know it exists too, but it's just not with A and B. Well, that's a lot to have to go through looking at these sets. Or I can look at the Venn diagram, and like it's pretty straightforward. 1 and 6 actually aren't in A or B, so that's why they're hanging out outside. 2 is only in A, 5 is only in B, 3 and 4 are in this intersecting part, so that means they're in both B and they're in A as well. So they're in both A and B, and everything again is contained within that box because everything is part of that universal set. This little symbol here between the A and the B, that's for an intersection. That's the symbol that you use. So if you ever see this, that means the intersection of A and B. So it would just be asking for the list of numbers that are in that intersection. And again, down here, you've got some more of that syntax, which starts throwing people off, but it's really like easy to understand. You just might have to reread it a couple of times and understand what, like, to comprehend what it's saying. So the intersection of A and B equals X. So these are like your elements. X is like these numbers that are making up the set, elements. So again, the intersection of A and B are your elements of X such that X is contained within A and X is contained within B. In other words, the intersection is going to be made up of all your elements, X, such that, this is like the restriction here. This is us putting a parameter on it, like, yeah, it's going to be made up of these numbers that you got, but specifically the numbers have to be in A and they have to be in B, which is 3 and 4.
So the intersection of A and B contain the elements 3 and 4. And now let's talk about the union of sets. The union of A and B is the set of all elements in set A or set B. So A union B is equal to all the elements X such that X is contained within A or X is contained within B. So the big difference between intersection and union is intersection we have an and, union we have an or.
Okay, so I'm going to stop there. Yeah, that is a big difference. You have and, or, you have or. And he just kind of said that just sort of like as an aside, like, yeah, intersections have and, unions have or. That's actually a really big deal. If you have the word and, that means that it has to exist in both places. If it says or, that means it can be in one place or it can be in the other place. So generally when you have or, I don't say always, but generally when you have or, when you've got a union, you're going to wind up with a bigger set of numbers because you're no longer being restricted to like one specific region. So in this case, what you're about to see is it's not going to be where A and B overlap. It's going to be whatever numbers exist within A and B all the way across. And notice I just used the word and to say within A and B. And that's where you got to be careful with us using like the English and us using and versus us talking about the math syntax. So when this says A or B, it's saying all the numbers that are in either B or A, which means it winds up being all the numbers within A and B. Whenever you have an intersection, what that is saying, only the numbers that exist in A and B. So on that previous slide, that's why it was 3 and 4, because that is only the numbers that are in both. In this case, it is all the numbers that show up in one or the other.
Using the same sets as we did for the intersection example, it would look the same, except now the union would be all the elements that are in A or B. So we'd be talking about this entire region here, because an element only has to be in one of them in order to be in the union. So A union B in this case would be all the elements in the universal set except 1 and 6. So we'd have 2, 3, 4, and 5. And a couple things to mention about the empty set. Any set A intersected with the empty set will equal the empty set. And the union of any set A and the empty set will always be the set A.
All right, so sometimes you'll see this called the null set as well. And the empty set is exactly what it sounds like. Kind of like when you're counting with integers between your positives and your negatives, you have 0, which is kind of like a placeholder. It's neither positive nor negative, but we needed something to be between 1 and -1. So it's 0. Empty set, same idea. This is saying like, what if you've got theoretically a set that has no elements? So like, again, we're talking about numbers here, but elements are actually the way to think about it. These elements of the set, these things that make up a set, generally they're numbers. But what if you have a set? So think of like your curly brackets with nothing in it. Well, that would be the empty set. So here, the intersection of some set with the empty set. So what would a set have in common with nothing? Well, the set doesn't have nothing in it. So in other words, when we were talking about intersections before, you were able to pick out whichever numbers they had in common. So like if it's, in that previous example, it was 3 and 4. If you have some set, say 1, 2, and 3, where does that cross over a set that has nothing? It doesn't cross over it at all. So that is why your answer winds up being empty set, because they have nothing in common. Now, like the opposite of that would be, what if I have a set of numbers, say 1, 2, 3, where do they join? And like I join them, so the union with the empty set. Well, the empty set was nothing. If A was 1, 2, and 3, well, what is 1, 2, and 3 along with the empty set? You would have 1, 2, and 3 and nothing. So it's just 1, 2, and 3. So it equals A, which was your 1, 2, 3 in this case. We can talk more about that if need be, speaking to my classes directly here. But in my experience in high school mathematics, at least, you don't spend a whole lot of time with this, but you do need to think a little bit about what this means and try to remember these two rules, because that could be questions that pop up. All right, so I just went through that video. I'm not sure quite how long this has been running now, but I know it's been going for a good amount of time, but I wanted to actually walk through a video, kind of explain what you should be doing, and you can, whatever the length of this video winds up being, compare it to the 6.5 minutes. And actually just looking at it up there, it's 30 minutes long, which is crazy. That, it went that long and that I've been talking for that amount of time. But that just shows you how much interpreting there was to do in that one place. That's why when a teacher gives you like a quick video, sometimes it's not just to watch through the whole thing. Like sometimes you have to actually pause, think about what it's saying, and then make decisions based on that. So I hope you got something out of this. Even if you're not in my classes, hopefully this helps you kind of understand, well, sets, at least the very basics of them, but also just some of the little strategies you should be doing if you are watching a video. Pause frequently. Define any words that you don't actually know. If there's something you don't understand specifically about the video, don't just say, I don't understand the video. Actually write down what it is that you don't understand so that your teacher can actually help you. And 4, don't be afraid to rewatch the video. Don't be afraid to ask questions, and don't go try a graded assignment if you have no idea what just happened in the video. Another thought, you could always pause these videos before he actually works it out and try to work out the Venn diagrams yourself and then play the video and see if you did it right. In my mind, you should not go try a graded assignment before you've proven to yourself that you can at the very least get the examples that they do in the video for you. Hope everybody has a nice day, a nice week. Everybody stay safe. Mr. H out.